All right. So, okay, let me repeat it. For the first slot, I had n minus k choices. For the next one, I had n minus k minus 1 choices. And for this one, okay, total length is j. So, okay, I have, right, for this one, I have n minus j plus 1, right? And if j was k plus 1, then I would have n minus k. Yeah. Değil mi? K artı 1 uzunluğunda olsaydı c yerine k artı 1 yazınca n minus k olacaktı ki doğru şey o. Tamam. Okay. So here it should be n minus j plus 1. And of course, the number of such words will be just the product of these choices, right? I have n minus k choices for the first letter here, this many choices for the second letter, and this many choices for the last one. So the total number of such words will be just the product of this, possibilities. And it is just this one. Okay, so this finishes the proof. Corollary is this, the number of different words of length L. Oops, I am sorry. Okay, the number of different words of length L in H1 is equal what? We denote this number by n L in parentheses, and this will be what? So for the first letter, I have n choices. For the second letter, I have n minus 1 choices. For the Lth letter, I have n minus L plus 1 choices, right? For the first one, n choices. So you just subtract one less number from the length of the word, right? Yani 2 ise words of length 2 will be just n times n minus 1. Words of length 3, n times n minus 1 times n minus 3, no, n minus 2, and so on. Okay. Any questions? These are, I guess, things you remember even from elementary school, I guess. Okay. Let an be the set of set of all words of length n in H1. Let P be the set of these classes. Actually, we will call it a partition. So it's a partition, be a partition of the alphabet A. So we divide the letters into disjoint union of sets, okay? A partition. Okay. So here A is just union of these, and this is a disjoint union, is a disjoint union. Okay. Uh, two words A1 and A2 in AN. So AN is the set of all words of length n in H1 are said to be uh, P equivalent. Okay, P equivalent if for all j from 1 up to n, the jth uh, letters of A1 and A2 belong to the same CN. Here n can be anything. So we say that two letters are P equivalent if first letters belong to the same CI or CN. The second letters belong to some other CI or CN. Let's say first letters belong to C3, second letters belong to C5, third letters belong to C5 again, maybe. Okay. If this is the case, we call those two words P equivalent. The P equivalence class, this is an equivalence class, of course. I mean equivalence relation. The P equivalence class of a word A in AN is the set of all words in AN which are equivalent to A. Yani bir tane A word verildiğinde ona denk olan bütün word'lerin kümesi de A'nın P equivalence class olacak. Peki mesela let's see an example. So let A, B, C, D and E be the alphabet. Be an alphabet. sorry. Uh, and let C1 be this set, and C2 the rest. So A and E. So it's a partition. They form a partition of the alphabet, right? It's a disjoint union. Be a partition P of A. So P stands for the partition. Okay, this P equals P stands for the partition. Uh, then the words A, B, C, D, E, and E, C, B, D, A are P equivalent. What is that? The first letters A and E, they belong to the same set C2. Second ones B and C, they belong to C1. Third ones again B and C, they belong to C1. Uh, Fourth letters D and D, well, they are the same. And the fifth ones A and E, they belong to C2. So these are P equivalent letters, sorry, words. And here is a proposition. Okay, so let A and P be as in the above definitions. A is an alphabet. AN is the set of all words of length n in class H1, and P is a partition. And let K1, K2 up to Ki be the number of letters in the sets forming the partition C1, C2, Ci respectively. Uh, then the number of different P equals classes of AN is what? The number of different equivalence classes. Okay, it is this number, and choose K1, K2. I have commas between K's, K1, K2, Ki minus 1. So what is this thing? It is just defined to be this number, n factorial divided by K1 factorial, K2 factorial, and Ki minus 1 factorial. No, it is defined to be the K minus 1 factorial and Ki factorial. Here, of course, where K1, K2, Ki adds up to n. In the notation, note that I have I minus 1, but here I have also ki k the I term also. So ki factorial is included here. Proof. Note that note that each p equivalence class has how many letters are words? Well, uh, okay. So each okay. Okay. Yeah, we are using all the letters. All the letters. So we are looking at uh, words of length n, so that uh, you know uh, okay, so let's say first K1 letters are from the partition set C1. The next K2 are from C2 and so on. So in each equivalence class, we have K1 factorial, K2 factorial, and Ki factorial uh, words, or uh, and so the number of equivalence classes, no, the number of elements in each equivalence class is constant. Okay, is constant. Uh, no matter what the words are, uh, the equivalence class for any word has the same number of uh, words or elements, and in total we have n factorial words of length n, right? Because I have n letters and I am counting all the words of length n, and no letter will be repeated. Therefore, there are n factorial letters, words. Since an has n factorial elements, the number of p equivalence classes is n factorial divided by k1 factorial, k2 factorial, and ki factorial. Değil mi? Yani her bir denklik sınıfında aynı sayıda eleman var. En faktöriyel tanede e, eleman olduğuna göre bunları eşit şekilde böleceksek o zaman kaç tane şey olur? Class olur. İşte her bir class'taki eleman sayısını alacağım. En faktöriyeli ona böleceğiz. Okay. Since we are considering only words of length n, each word should contain all the elements in each CI, okay? And of course, you know, so you have, let's say, something like this, and these elements are from C1 and these elements are from C2. So I have how many choices? Well, 3 factorial choices here and 3 factorial choices here. So 3 factorial times 3 factorial. Uh, I have I may have another word of, let's say, length 6 again, and this time the first letters, 3 letters are from C1, the last 3 letters from C2, but doesn't matter. Again, the number of equivalence, the number of elements in the equivalence class of this word again will be 3 factorial times 3 factorials. So it doesn't matter how these letters are distributed in the word. The number of elements in each equivalence class is always 3 factorial times 3 factorial. Okay? Yani şöyle, şimdi so in this example I choose n equals 6 and I have, let's say, two uh, my alphabet is divided into two sets. Each has 3 letters, and we consider uh, words of length 6. So I will use all the letters. Suppose I have a word like this where the first, third, and fifth letters are from C1 and the rest are from C2. What is the number of elements in the equivalence class of this word? Well, since they will be equivalent to this word, uh, this letter will be from C1. This letter also will be from C1 and this one will be from C1. And I have 3 letters in C1. So I just plug 3 letters into 3 boxes. There are 3 factorial choices. And the same for the other 3 letters. So the equivalence class of this word has 3 factorial times 3 factorial elements in it. What about this word? Suppose the first 3 letters are from C1 and the last 3 letters from C2. Again, the same logic will apply here. Okay? Because any word which is equal to this one should contain the first 3 letters from this set C1, and the rest of the letters will be from C2. Again, I have 3 factorial times 3 factorial elements. Okay? Different equivalence classes, but each equivalence class has the same number of elements. Therefore, the total number will be just 6 factorial divided by 3 factorial times 3 factorial. Tamam mı? Okay. So that's the proof. It helps, when you just think of the proof on a specific example like this one. Otherwise, there are just too many words and it may just get complicated real quick. All right, so another corollary. Siz de bir derste aslında 2 farklı ders dinliyorsunuz. Okay. Let's see be a subset of the alphabet A, and let's consider the partition consisting of C and its complement. Actually, just as in the example I talked about. Of course, these two sets gives a partition of the alphabet because you have some elements and then the rest. If, let's say, the number of elements in C is K, then the number of P equivalence classes in AN is what? It is just n factorial divided by k factorial and then n minus k factorial, right? Like this one. K1 and K2, I have K1 and K2. Their sum is n, and K1 is just K, therefore K2 is just n minus K. But we know that this number has another name, right? This is just called n choose K. Because when you choose K elements, you also choose n minus K elements, because in total you have n minus K elements. All right. So that's an immediate corollary. And then we have a proposition. This time we consider words of type or class H2. So repetition of letters is allowed. So let A be a such word. So an element of H2 have a length K. Then there are n different words of length plus 1 in H2 having uh, A as its initial expression. In particular, the number of words of length K in H2 is what? Is just n to the power K, because you can put each time any letter from the alphabet, and the alphabet has n elements. So for each choice you have, for each slot you have n choices, and you have k slots, so you have n times n times n times n to the power k choices. Okay. İspatına gerek var mı bunun? This is, I guess, clear, right? You don't need to write down a proof. Uh, Here is another proposition. Oops, zamanı geçirmişiz gene. Alright. Yeah, let me stop here. This says a proof. I have to write down the proof, and it will take some time. So let me stop here. All right.